Hi, I'm Drew.
And I'm Aaron, and this is our entry to the Faculty of Natural Sciences Science and Innovation competition. We're going to be looking at clean water and sanitation.
In 2024, global access to water, sanitation, and hygiene remains critically inadequate, with 2.2 billion people lacking safely managed drinking water, 3.4 billion without safely managed sanitation, and 1.7 billion without basic hygiene services at home. These gaps place immense pressure on public health systems, economic productivity, and social equity, particularly in low income and climate vulnerable regions. At the same time, water systems are increasingly strained by pollution. Rising water stress and weak governance, with industrial discharge, agricultural runoff, and untreated sewage degrading water quality worldwide. Currently, only 56% of domestic wastewater is safely treated, representing both a serious environmental risk and a missed opportunity for water reuse and resource recovery. As climate change intensifies, droughts and floods and demand continues to rise, progress towards Sustainable Development Goal 6 remains off track, with sustainable water management unlikely to be achieved before at least 2049.
Addressing this challenge and achieving Goal 6 requires mobilizing comprehensive financial mechanisms, leveraging innovative technologies, strengthening institutional capacity, and fostering multi-stakeholder partnerships. And it also requires the integration of water management across all sectors and governance levels.
Global water stress remained very unsteady, at roughly 18% in 2022, which had been the same since 2015. But due to regional climate change, the disparities are stark. Many countries in North Africa and Western Asia, and Central and Southern Asia, face critical water stress levels exceeding over 75%. Northern Africa and Western Asia have also experienced a mildly concerning 12% increase in water stress since 2015. About 10% of the global population now live under high or critical water stress.
Economic sectors play a key role in shaping water stress levels. In 2022, agriculture accounted for 72% of the global freshwater withdrawals, followed by industry, 15%, and services, which were 13%. While essential for food security and economic growth, agriculture is both a driver and a casualty of water stress, making it one of the most vulnerable sectors.
As shown by the graph, global progress on integrated water resource management (IRWM) remains slow, with implementation rising from 49% in 2017 to 57% in 2023. While 47 countries (26%) have reached or are close to the very high implementation target, 73 countries (around 40%) are being left behind. Insufficient financing remains a major barrier between whether they've been able to implement this or not, where 60% of countries lack effective revenue raising mechanisms and about 70% report inadequate funding for water management at subnational levels.
So, let's talk about our solution to the problem of unsustainable and unsafe drinking water. Together, we have conceptualized an AI water hub that integrates ceramic filtration, activated carbon, and UV purification into a single solar powered system capable of producing safe drinking water in a sustainable and energy independent way. By using artificial intelligence, the hub continuously evaluates real time sensor data such as bacterial indicators, turbidity, and pH, allowing it to monitor water quality and system performance at all times. This data can be used to trigger automatic alerts for a mobile application or notify local authorities and government bodies responsible for managing the system, enabling rapid response to emerging issues. Crucially, AI driven analysis allows maintenance needs to be predicted before failures occur, ensuring uninterrupted access to clean water for more people. During periods of rainfall, the hub can also harvest and store rainwater, reducing reliance on groundwater reserves, increasing system resilience, and supporting a more sustainable and adaptive water supply.
Now, the science behind our idea. The World Health Organization has four key criteria for water to be deemed safe. 0 E. coli per 100 milliliters, less than 5 nephelometric turbidity unit, pH of 6.5 to 8.5, minimal chemicals, e.g. nitrates, heavy metals, pesticides. This is why we have 3 different methods in order to clean our water, to make sure that our water is as safe to drink and as sustainable as possible. Then we would need to monitor the pH to prevent pipe corrosion and metal leaching, as if water is too acidic as well, it is bitter tasting water if it is alkali. To do this we can use calcite. Turbidity must also be monitored, else it will shield bacteria from the UV light.
So let's take a look at the first step, which is ceramic filtration. So ceramic filters function through a physical filtration process based on microscopic pores, typically measuring between 0.2 and 0.5 microns, which is small enough to block most bacteria and suspended solids from passing through. This process is governed by the size exclusion mechanism, where contaminants larger than the pore diameter are retained on the surface, or within the structure of the ceramic material, while water and smaller particles are able to flow through. As water passes through the filter, bacteria accumulate on the filter surface, forming a layer that can further improve filtration efficiency over time. However, because many viruses, dissolved chemicals, and some fine particles are smaller than pore size, ceramic filtration alone cannot fully eliminate all contaminants. For this reason, additional sanitization steps are required to inactivate or remove the remaining pathogens and ensure that the treated water meets safe drinking standards.
Now, onto activated carbon. Activated carbon is a form of carbon that has been specially processed to create millions and millions of microscopic pores. This gives it an extremely large internal surface area, about 1,500 square meters per gram. This vast surface area allows the activated carbon to remove contaminants through a process known as adsorption, which differs from absorption in that molecules adhere to the surface rather than being dissolved into the material. The carbon surface is largely nonpolar and interacts with contaminants through weak electrical forces, known as van der Waals forces. Many common water contaminants, such as organic compounds, chlorine, pesticides, and certain industrial chemicals, are carbon-based and either nonpolar or slightly polar, making them naturally attracted to the carbon surface. As water flows through the activated carbon, these contaminate molecules bind to the pore walls, while cleaner water continues to pass through, resulting in improved taste, odor, and chemical quality of the water.
Okay, now on to the final filtration stage, and that is UV LED purification, which inactivates microorganisms rather than physically removing them. Ultraviolet light disrupts the genetic material of bacteria, viruses, and other microbes, preventing them from reproducing and effectively rendering them harmless. The most effective wavelength is between 260 and 265 nanometers, as this range is strongly absorbed by DNA and RNA. When UV photons penetrate microbial cells, they damage the DNA by causing abnormal bonds to form between nucleic acid bases, particularly thymine, which interferes with the replication and cellular function. In practical system design, this process can be implemented using an UV LED positioned above the water flow path, combined with stainless steel or UV reflective interior surface to maximize light exposure and disinfection efficiency, ensuring a final layer of protection against remaining pathogens.
Now, pH control. We thought we'd try use calcite to control pH, as calcite is a natural occurring mineral composed of calcium carbonate and is commonly used to stabilize water chemistry by neutralizing the acidity. When acidic water comes into contact with calcite, a chemical reaction occurs in which calcium carbonate reacts with the hydrogen ions, forming dissolved calcium ions and bicarbonate, as shown by the reaction CaCO3 plus H plus producing Ca2 plus and HCO3 minus. By consuming hydrogen ions, this process raises the pH of the water, reducing acidity and corrosiveness, while also improving taste through the addition of beneficial calcium minerals. Calcite dissolves more rapidly in acidic conditions because higher concentrations of hydrogen ions drive the reaction forward, allowing faster neutralization. As the pH increases and the water becomes less acidic, the availability of hydrogen ions decreases, causing the rate of calcite dissolution to slow naturally. Once the water approaches a near neutral pH, the reaction effectively self-limits and stops, preventing overcorrection and maintaining a stable and balanced water chemistry.
So now we're going to take a look at the use of AI. So we can use AI for monitoring, prediction, and supporting decisions to keep the system reliable and sustainable across multiple countries and residential and governance levels. So we have some sensors continuously measure key water parameters. These are pH, turbidity, flow rate, UV LED intensity, and system temperature and power status. These values can be logged over time, creating a performance history of the system. The AI identifies deviations from normal behavior earlier than a human operator could, meaning if a gradual rise in turbidity is found, it may indicate a clogging ceramic filter, or a slow drop in UV intensity may indicate LED aging. Abnormal pH drift may indicate depleted calcite media, or sudden changes may signal contamination or system damage. AI can also predict when components need maintenance before failure occurs, reducing downtime and preventing unsafe water from being distributed. Estimating remaining life of filters, predicting when calcite media needs refilling, scheduling UV LED replacement, and identifying pump or flow issues are all features that AI could be used for in this system. When unsafe conditions are detected, the system can automatically stop water dispensing. Alerts can be sent via SMS or a simple phone app, and clear maintenance instructions could be provided to trained local technicians, allowing a quick response that keeps everyone using the water safe.
Now, a little summary of what we have discussed. This system that we have thought of uses a multi-stage water treatment process that combines physical, chemical, and digital safeguards to ensure consistent water quality and system reliability. Ceramic filtration serves as the first barrier, removing suspended particles and most bacteria through size exclusion, followed by activated carbon, which absorbs chemical contaminants, chlorine and organic compounds while improving the taste and odor. Calcite then passively stabilizes water chemistry by neutralizing acidity, raising pH, and reducing corrosiveness without the risk of overcorrection. UV LED purification lastly provides a final disinfection step by inactivating any remaining microorganisms at the genetic level, preventing reproduction and ensuring microbiological safety. To maintain performance over time, an AI-assisted monitoring continuously analyzes real-time sensor data, including pH, turbidity, UV intensity, and flow rate, to detect anomalies, predict maintenance requirements, and identify system degradation before failures occur. Automatic alerts and built-in safeguards prevent the distribution of unsafe water, while the integration of rainwater harvesting reduces dependence on groundwater sources, enhances system resilience, and supports more sustainable water management.
So now we're going to look at cost. We've estimated on a residential scale the total cost of implementation would be around 3,000 to 14,000. Cost depends on a variety of factors, including the scale of the system, water source quality, energy and maintenance, and compliance with government policies. On a governmental scale, we think the total cost for implementation could be around 20 million to 80 million pounds. Considerations for government deployment would be capacity planning, regulatory compliance, maintenance, and lifecycle costs. This is relatively cheap for governments to implement, so could be done around the world, especially in developing countries where these technologies are most needed.
Now, on to sustainability, which was one of our aims. This project is designed with sustainability as a core objective, aiming to maximize the use of naturally available water sources while avoiding excessive pressure on the surrounding environment. By prioritizing rainwater harvesting, the system captures and purifies the water that would otherwise be lost as runoff, providing a reliable supplementary supply without increasing demand on groundwater reserves. In addition, the system is intended to treat water sources that are typically considered undrinkable, such as contaminated surface water or low quality collected water, by purifying them to safe standards using the multi-stage treatment process. This approach not only expands usable water availability, but also significantly reduces overall water waste, promotes resource efficiency, and supports long-term water resilience in a way that aligns with environmentally responsible water management.
Finally, we're going to look at health. According to the World Health Organization, drinking polluted water can lead to a wide range of serious health consequences, including infections, certain cancers, and cardiovascular conditions. Contaminated water often causes acute gastrointestinal symptoms, such as severe diarrhea, nausea, vomiting, and abdominal pain, while some waterborne infections can also result in fever, jaundice, and skin rashes. In more severe cases, exposure to unsafe water can cause life-threatening diseases such as cholera, typhoid fever, giardiasis, cryptosporidiosis, and dysentery, particularly among children, the elderly, and the immunocompromised individuals. By addressing physical contaminants, chemical pollutants, and microbial pathogens, our three-step purification system is designed to significantly reduce these risks and ensure that the treated water is safe consumption by anyone.
Thank you
Thank
for
you for
listening.
listening.